So this is class 7 of cryptography and network security. In this class, we will discuss about different concepts of classical number theory. That we know that uh, the cryptography and network security is one of the applications of number theory. A number of concepts, algorithms, and theorems are used in cryptography. So whether it is advanced encryption standard AES algorithm or elliptical curve algorithm idea or a public key encryption methods. So everywhere the number theory is used. So today we'll discuss about the groups, rings, fields from the abstract algebra. So here, constant operations and numbers, where what constitute a number and the type of operations varies considerably. Yeah. So a group. Group is a set of elements or numbers. Group is a set of elements or numbers with some operation whose result is also in the set of closure. It obeys associative law, that means A dot B parenthesis dot C is equal to A dot B dot C parenthesis. This is associative law. Every element must have some that means that obeys has identity E. Even that is E dot A is equal to A dot E, that is equal to A. For let's say 1 is the identity in Z real number, so that E dot 1 is equal to E. Sorry, that is A dot 1 is equal to A, and 1 dot A is also equal to A. So that is has an inverse. That means suppose here E is the identity. So A dot A inverse must be equal to that identity. And commutator must be commutative. Commutative means A dot B is equal to B dot A. Then the group formed an abelian group. So if the commutative law is satisfying in a group, then it is known as abelian. So once again, a set of elements or numbers, that is a group, with some operations whose result is also in the set. That means there is a closure property. That means if I will perform multiplication, let's say 2 is one number and 3 is another number. So both are present to the set of integers. So 2 into 3 is also another number. That means that is also belongs to that set of integers. So in that case, we can say that is a group. Okay, it obeys associative law, identity, as inverse, and if that is commutative, then it is known as a abelian group. Then a cyclic group. Define exponentiation as a repeated application of operator. Let's say a to the power 3, that is a into a into a. And let the identity be E is equal to a to the power 0. A cyclic group, a group is cyclic if every element is a power of some fixed element. That means if B is equal to a to the power k. For some A and every B in group, A is said to be a generator of the group. Okay. So a ring. Ring is a set of numbers with two operations, addition and multiplication, which form an abelian group with addition operation. Okay. So what is abelian group? Previously we have discussed. So if that is commutative, then we can say that is one abelian group. So here the ring with two operation, addition and multiplication, forms an abelian group with addition operation and multiplication. And in multiplication, it has closure. Closure means the resultant must be present in the same set, is associative, and distributed over addition. The multiplication must be distributed over addition. That means A dot B plus C is equal to AB plus AC. If multiplication operation is commutative, it is known as commutative ring. If the multiplication operation is commutative, it is forms an commutative ring. If multiplication operation has an identity and no zero divisors, if multiplication operation has an identity and no zero divisors, it forms an integral domain. So, what is integral domain? So, that is if multiplication operation in a commutative ring has an identity and no zero divisors, it forms an integral domain. So, filled. A set of numbers with two operations which form abelian group for addition and abelian group for multiplication have hierarchy with more axioms or laws, that is of group, ring and feld. Okay. So next is modular arithmetic. Defines modulo operator A mod n. Defines modulo operator A mod n to be reminder when A is divided by n. When A is divided by n, suppose A is 11 and n is 5. So that A mod n. Okay, this percentage is also known as this mod is equal to the remainder. That means here 11 divided by 5, so 2 and 8. 1. So 1 is the remainder, so the result will be here 1. We will perform this. So depend modulo operator A mod n to be remainder when A is divided by n. So when A is divided by n, this is the quotient and this is the remainder. So the remainder will be the result of modular operation. In modular operation here, modular division, you can say this is right. So use the term congruence. Use the term congruence for A is equal to B mod n. A congruent to B mod n. A congruent to B mod n. That means when divided by n, A and B have same remainder. Get it? So that is congruence. A congruence, sometimes it is equals or sometimes it is 3 bars are there. So use the term congruence. But A is equal A congruent to V mod n. That means when divided by n, A and B have the same remainder. Let's say, for example, 100 is equal to 34 mod 11. That means 100 mod 11. The remainder is 1. And the 34 divided by 11. Also, the remainder is 1. So, if the remainders 2 or 1, if when divided by n, if A and B having the same remainder, then we can say A is congruent to B. Here A is equal to 100 and B is equal to 34. So, you can say A is congruent to B modulo 11 or the modular field of 11. So, 100 is congruent to 34. Right. So B is called a residue of A mod n. B is called a residue of A mod n, since with integers can always written as in this format: A is equal to Qn plus B. Okay, so we can call it this as a residue or remainder. Usually choose the smallest positive remainder as residue. Usually choose the smallest positive remainder as the residue. That means the residue B must be more than equal to 0 and less than equal to n minus 1, where n is the division. The process is known as the, if we perform this operation repeatedly, the process will be known as modular reduction. The modular reduction, suppose here minus 12 mod 7 is equal to, that we can say minus 12 plus 7 mod 7, that is here it is minus 5. Then for this minus 5 plus 7 mod 7, that is equal to my plus 2. Then 7 plus 2 mod 7 is equal to this 9 mod 7. So this process of reduction is known as modular reduction. Okay. So the divisors. Say non-zero number B divides A. Say a non-zero number B divides A. If for some M of A is equal to M into B and A, B, M all integer, that is B divides into A with no remainder, denotes B by A, and we say that B is a divisor of A. For any integer, so say non-zero number B divides A. If for some value of M, we can write A is equal to MB. That is B divides into A with no remainder. So that is denoted as B divides A. Okay, and say that B is a divisor of A. For example, here 24. 24 is divisible by 1, 2, 3, 4, 6, 8, 12, and 24 itself. So all are the divisor of 24. Already you know everything in discrete mathematics. Modular arithmetic. Modular operation is a clock arithmetic. That means after certain number, it will once again it will be repeated, cyclic. Uses a finite number of values and loop back from the other end. The modular arithmetic is when do addition and multiplication and modular reduce answer. Can do reduction at any point of time. That means A plus B mod n is equal to A mod n plus B mod n whole mod. Okay, can do modular arithmetic with any group of integer, form a commutative ring for addition with a multiplicative identity. Note some peculiarities. If A plus B is equal to A plus C mod n, then B is congruent to C mod n. If A plus B is equal to A plus C mod n, then B plus B is congruent to C mod n. But if A dot B is equal to A dot C mod n, then B is equal to C mod n only if A is repeatedly prime to n. Understood? But if A dot B is equal to A dot C mod n, B is congruent to C mod n if A is relatively prime to n. That means here relatively prime means the GCD of A and n is equal to 1. The greatest common divisor of A and n is equal to 1. Then we can say that is relatively prime. Relatively prime. Okay, so if a dot b is equal to a dot c mod n, then b is congruent to c mod n only if a is relatively prime to a. So this is so next. Let's see the modulo 8 addition. For example, so 0 plus 0 is 0, 0 plus 1 is 2, 1, so 0 plus 7 is 7. Now 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 6, 7, so modulo 8, 7. Now 1 plus 7 is 8. So 1 plus 7 is 8. So 8 mod 8 is equal to 0. So that is 2. Similarly, this 2 plus 5 is 7. 2 plus 6 is 2 plus 6 is 8. So 8 mod 8 is equal to 0. And 2 plus 7 is 9. 9 plus 2 plus 7 is 9. So 9 mod 8 is equal to 1. So 9 mod 8 is equal to 1. So similarly, 3 plus 5 is equal to 8, 0 to 9. That is 9 is equal to 1. So 10 is equal to 2. So this is the process, right? So modulo 8 addition. So in the next class, we'll discuss about the greatest common divisors. In the next class, I'll discuss with you the greatest common divisor and Euclidean algorithm to find out the greatest common divisor of two numbers.